Okay, everybody, I think this is going to be a really helpful video, but I sincerely apologize for however long it is going to end up being, because I'm going to choose many of the examples in the Unit 3 review to go over. It says very specifically at the top that they're not in any particular order, and I want to stress that I'm going to explain why I understand the type of problem based on the wording I see, okay? Hopefully this will be helpful. Note that I may not do everything identically to how it's written out in the solutions online, but all of these solutions are available online. And some of the problems I will not go over. So let's just go, we're going to dive right in. The company that produces snack foods used the machine to distribute 454 gram bags of pretzels. A simple random sample of 25 bags has the following weights. All right, so let's just begin by looking at the glaring idea that we're given a list, which can also be referred to as data. It's a single list, so this has to be a t-test, and it will be on data. Knowing that this is true, I already entered this list into my calculator, so at this point you may want to pause the video and just quickly enter that into list 1. This says, does the data provide sufficient evidence to conclude the packaging machine is working properly? Okay, so for a t-test on data, we only have to figure out what mu naught is. And that's the only other value given besides the n provided. So that's right here. This is the amount that the packaging machine is supposed to put in. We are determining if it's working properly. So the machine is either putting the right amount into the bags or it is not. So we're going to say mu equals 454 grams. Or if it's not working properly, right, then it doesn't equal 454 grams. So we believe that the mean number of grams is this, and we believe maybe it's not working the same way as it should. So we go and we run a t-test on data, and we put the 454 into mu naught. So you take your calculator. Remember that we already entered the data in. We go to our stat and our test menu. And this is just a regular t-test, so it's number 2, and it's on data, so make sure you have data highlighted, and we need to make mu naught 454. Our data is in list 1, and we would like to select not equal to, and then hit calculate, okay? So I'm going to go ahead and round this out to negative 2.3584, so t equals negative 2.3584, and my p-value, which I have right here in the calculator, is 0.0268. So I'm going to go ahead and compare this to, okay, there is no alpha level. Whoops! All right, so I guess we should be assuming 0.05. So we're going to assume alpha is 0.05, and this p-value is in fact less than that alpha level. Okay, no. You were just outside. I really want to show everybody what's happening, but my camera doesn't just move that way. My dog just stood up against the window to try to go outside. Okay, so our p-value is less than our alpha level, which means we get to reject the null, okay, and we make our conclusion here. So there is enough evidence to show, and remember, we say, is it working properly? Well, if it equaled 454, it would be. We showed that it was not equal, so there is evidence to show the machine is not working properly. Okay? I can say this, or I can say that the mean weight is not 454 grams. Okay, what assumptions and conditions did you need to check for your test? So there are 3 for t-tests. Independent/randomization. So we're going to check up here in the wording. A simple random sample of 25 bags has the following weights. So I'm going to write in quotes SRS and then put a check mark next to it because I know I met this condition. The second condition we have to check is nearly normal. which means we have to check a histogram. No. Oh, my dog, here, he's trying to get into the video. Hello. Hello. Okay, so to check the histogram, we would go to second y equals and go to your stat plot menu, something we haven't done since Unit 1. Make sure that you go here and turn your first plot on. And we are supposed to check a histogram. So choose the plot that looks like the histogram. It's the third plot. My data is in list 1, and I hit zoom 9. So we would refer to this image as, I hope you can see that. I really don't know what the best way to hold this. Oh, it actually looks quite good in the picture now that I turn my head. This image would be referred to most likely as semi-symmetric, right? It looks slightly skewed to the right, okay? So we can say that it's slightly skewed. Therefore not met, perhaps, okay? And then in condition 3, that's the 10% condition. And they say they chose n equals 25. Do we believe that's less than 10% of all bags produced? Yes, they produce snack foods, so I guarantee that this is less than 10% of all the bags they've ever produced. So 2 out of the 3 conditions are clearly met. Many people would argue that this is symmetric enough to proceed with the test we did above and make accurate conclusion. All right, let's move on. I am going to go ahead and do number 2 as well, okay? So this says, the U.S. Substance Abuse and Mental Health Services conducts a survey on drug use by type and age group. According to the National Household Survey on Drug Abuse, that's a national survey, so the information that comes after is about the population. It says 13.5%. All right, I'm going to circle that. I'm going to draw an arrow to it, and I'm going to write that that's P0. Of 18 to 25-year-olds were current users of marijuana in 2000. So this is old information. A recent poll of 1,283 randomly selected 18 to 25-year-olds revealed 205 currently use marijuana. At the 10% significance level, or alpha of 0.1, do the data provide sufficient evidence to conclude the percentage of 18 to 25-year-olds who currently use marijuana has changed from the 2000 percentage? Okay, so they gave us one percentage and then a fraction. So this is a 1 prop Z test, okay? The percentage that's provided is from the population, and we need to find the fraction of people who said yes to the question being asked. In this example, the question being asked is, do you use marijuana, I guess, right? And then they said 205 out of the 1,283 did say yes. So back in 2000, the percent was 13.5, but now we got 205 out of 1,283 people saying yes. We would like to know if this has changed. So changed isn't good enough to give me a direction. It just says not equal to. So let's go ahead and make sure we understand that this is a proportion. It is currently, in 2000 it was 13.5. We believe it's no longer 13.5. So let's go to our calculator and run our 1 prop Z test. So turn this on, go to stat and tests. This is number 5. P0 is 0.135. X is 205. N is 1283. And we are not equal to. So if we run this test, we get, I'll write them over here so the calculator is still on the screen. Z is, so it has gone up. It's 2.5976 standard deviations above the mean. And the p-value is 0.0094, very small p-value. So we are comparing this to alpha of 0.1. So our p-value and our alpha level, so this was 0.0094, and alpha was 0.1. P is definitely less than alpha, which means we will reject the null. So we do have evidence to show the current percentage of marijuana users has changed. So there is enough evidence to show the proportion of 18 to 25-year-olds using marijuana has changed. Right, so that's all we're able to show. I mean, technically we did show that it increased by 2.6 standard deviations. However, the test results imply that it has changed. All right, I'm moving on to the next page. Example 3 is from the mixed up examples. So I will be skipping that and going on to example 4. Example 4, let's look at this. This is a contingency table. I need you to think this has to go into a matrix, okay? Which means that it is a chi-squared test, and we should figure out what kind of chi-squared test it is. Now, given that it's a matrix and that I only taught you one chi-squared test with matrices, then this would be a chi-squared test of independence. Okay, let's just make sure we really understand that that's what's being asked here. So it says, Democrats and Republicans were surveyed for their opinions on gun control. Results are shown below. So we've got, just to be clear, the inside of the table is technically the matrix. We would not include any totals that are given in our matrix. Based on the sample, does a person's opinion on gun control depend on party affiliation? So this is a test of independence. We want to test it at the 0.05 level of significance. So if it's a chi-squared test in independence, we can write our hypotheses right away. And then we can put the matrix in the calculator and run the test. So we believe in the null hypothesis that there is no change or they are independent. So that means opinion on gun control and party affiliation are independent. So we'll say on gun control and party affiliation are independent. And then this is the negation of that statement, right? So this says opinion on, I'm just going to say gun control and party affiliation are not independent. I'm just abbreviating so the video is not 2 hours long, okay? So this is going to be a chi-squared test on independence, which means we want to put the observed data into matrix A. And we have to check how many rows and columns there are. There are 2 rows and there are 3 columns. So we're going to make a 2x3 matrix out of this information. So I'm going to remind you guys how to do that. So I'm going to scoot this up so we can all see the calculator. That means that we need to go to second matrix and go to edit. So choose edit and select matrix A. I'm now going to change this into a 2x3 matrix, which automatically adjusts the size, and the values are entered by row. So you have to enter them by row. 440, 400, and 120. And then remember, we don't include the totals, so we just want to include the 2 rows inside here. Okay? Once that's entered, you can quit out of there. Now go to your test. Stat. Arrow left to test, and always arrow up for chi-squared. This is the regular old chi-squared test, so hit enter. Observed is A. Your calculator automatically generates the expected value matrix B, and here we can go to calculate. Wow, chi-squared is huge, and our p-value is nice and small. So let's go ahead and record these 2 values. So our chi-squared is 26.129. I'm going to go 5 so that I don't round that to something awkward, okay? And then our p-value is 2 times 10 to the negative 6, okay? And I said we could kind of theoretically, I kind of consider these approximately 0, or you can write this out as many decimal places as it has. So I'm going to get rid of the calculator because we can make our conclusion now. This p-value is definitely less than an alpha of 0.05, and we therefore will reject the null. and we can conclude that opinion on gun control and party affiliation are not independent, which is the same here as dependent. Okay, so yes, what we probably expected, right? The party affiliation you have does actually depend, these two variables depend on one another is what I'm trying to say. Our party affiliation and opinion on gun control are typically related. Now, what assumptions and conditions did you need to check for your test? We were supposed to check that this was random. That these are chi-squared tests. So our conditions for chi-squared tests were randomization first. So I think this is the list I gave us in the notes in order. So randomization, it's not stated if you go back and read the wording up here, right? It just says they were surveyed. It doesn't say that it was a random sample. The second condition is, were the data counted data? And this is really, we're looking up here, are these whole number counts? Yes, they're all counts. Okay, we can say that this is met, but condition 1 wasn't stated. And the third condition is expected cell frequency. So we look at matrix B for this one, okay? So we go to our calculator, and we say, well, I just want to stare at matrix B and make sure all the values. So now look at this. I have 2 matrices when before I had none that were filled in. I can just here go down to B, and once I hit enter, it appears on my home screen, and I can hit enter again, and I can see the values and arrow right to check. All of the values in B are in fact larger than 5. All values are greater than or equal to 5. So we can put a check there that this condition was met. All right, great work. Let's move on to the next one. So we're on to page 24. And I guess I'll be doing everything on this page because I've checked off all of it. So here we have 38% of a random sample of 1,012 American adults believe in ghosts. This should sound familiar because this is a problem from class. It's just so old that I want to redo it. So this is a random sample percentage, so that's p hat, and this is the number of people in the sample, so that's n. It says find the margin of error if we want to be 90% confident. So I know that there's a formula for margin of error, but I also know that it's actually much easier if we use this formula. So it's upper bound minus lower bound over 2. So we can't do that until we find our confidence interval first. So we first have to find a 1 prop z interval using an x, which is 0.38 times 1012. So I'm going to do that over here because I can't remember what the answer is. And we round appropriately, so we round that to 385 people, and we say that n here is 1012, and our confidence level is 0.9. So I'm going to go to my calculator. Stat, arrow left to test, and it's a 1 prop z interval, so that's actually all the way down at letter A. N is 385. X is 385, N is 1012, and my confidence level is only 0.9, so that might need to be adjusted. The interval here we get is 0.3553 and 0.4055. Okay. So then I can come back over here and compute the margin of error using this formula, but I'm going to write that work here where it's a little bit clearer. So 0.4055 minus 0.3553 all over 2. Well, good Lord, I did that wrong. Hello. Okay, let me fix that. Okay, that's definitely more reasonable. 0.0251 is our margin of error here. Okay, that's 2.5%. Explain what a 90% confidence interval means and find the interval. Oh, well, we did that. 0.3553 and 0.4055 And let's interpret this interval for practice. I am 90% confident that the true proportion of adults who believe in ghosts falls between, now we write these percentages, right? Let's say 36% and 41%. We'll just round them for the sake of this problem, okay? You can leave these as decimals and you don't have to convert them into percentages. Don't worry about that. You can say the proportion lies between and then leave them as decimals. It's totally up to you. Now, this is the reason why I really wanted to do this problem for this part right here. It says what sample size? Like that wording right there says I need to find n. Okay, and you're saying, well, there already is an n up here. Yes, but now that we're going to change some stuff around. It says what sample size would be needed to reduce our margin of error to within 1%. So now they're telling me my margin of error is 0.01, but I want to keep my 90% confidence. So my confidence level is 0.9. So I'm now going to need this formula. Z star squared times p hat times q hat all over the margin of error squared. Okay, so this is something that we did in chapter 16. Well, I know the margin of error, and I actually do know p hat. So p hat is 0.38, which means I subtract from 1 to get q hat, so that's got to be 0.62. The margin of error is 0.01, and z star is for the, I'm going to write it as 90% confidence, right? That's 1 point, and this one was 645. So I'm going to go fill in our formula. N equals 1.645 squared times 0.38 times 0.62, all divided by 0.01 squared. And we're going to round that up always. So 1.645 squared times 0.38 times 0.62 divided by 0.01 squared. And we always round this up. So this decimal would end up being like a 0.4, but I don't care what it is. I'm always going to round that to 6,376. Who are these people? Adults. American adults. That's who we're surveying. Okay? All right, let's move on to the next question. If you are nervous about this one, I would definitely put this as well as the Z star chart on my note card, okay, to go with it. All right, let's move on to example 6. Within a school district, students are randomly assigned to one of 2 math teachers. So that sounds like 2 groups, okay? Let's read on, but that sounds like what we're going to see here. It's Mrs. Smith and Mrs. Jones. After the assignment, Mrs. Smith had 30 students, Jones had 25. At the end of the year, each took the same test. Mrs. Smith's students had an average test score of 78 and a standard deviation of 10. We should just stop here. They mentioned the keyword standard deviation. So not only is it 2 groups, but they mentioned 2 different standard deviations and 2 different averages, which means that this is a 2-sample t-test on stats. So we're going to need to write down a long list of information to enter into the calculator. But let's see what we're testing first. It says, test the hypothesis that Mrs. Smith and Mrs. Jones are not equally effective teachers. Use a 0.05 level of significance. Assume the performance is approximately normal. So they're helping us meet our conditions here by assuming it's normal. So let's see what we need to record. If you need to, check your calculator, but we're going to need to know who group 1 is and who group 2 is. And we're going to want to, let's go in order. So we'll do Smith first and Jones second. So we need X bar 1, S1, and N1, X bar 2, S2, and N2. So let's read. Mrs. Smith had 30 students. Mrs. Jones had 25. Mrs. Smith's average was 78. and her standard deviation was 10. Mrs. Jones's average was 85 with a standard deviation of 15. And we are testing whether they are equally effective, right? So the idea is that we believe they are equally effective if there has been no change. And, oops, that should be a 1, sorry. And they are not equally effective if there was a change. So let's go ahead and run our t-test. So we'll get a t and a p-value. And I write too big, but hopefully I'll be able to fit a little conclusion in here. So we're going to do a t-test, a two-sample t-test, which is number 4. Let me move this over. We're doing this on stats. So x bar 1 is 78, S1 is 10, and N1 is 30. X bar 2 is 85, S2 is 15, and N2 is 25. And we are testing whether they are or are not equally effective. So it's not equal to, we always say no for pooled, and we hit calculate. So I'm going to record the t, negative 1.9932, and a p-value of 0.053. And we're supposed to compare that to 0.05, so that is actually larger. So let's do that over here. My p-value of 0.053 is in fact larger than 0.05, so that means we fail to reject the null. Okay, so unfortunately what we have to do here is write a sentence that says we failed our experiment. So there isn't evidence to show the teachers. Remember, we were trying to show they are not equally effective, are not equally effective, right? So we tried to show that they were not, we failed. And now we keep going. Find a 95% confidence interval in the average student exam scores between the two. So then we do a 2-sample t-interval on stats, and the confidence level is going to be 0.95. So let's go to our calculator. Stat, arrow left to test, and you want to do a 2-sample t-interval, which is 0. And your calculator knows all of the information. We just need to arrow down and change the confidence level to 0.95. Make sure that there's no pooled, and then hit calculate. So we record this information. Negative 14.1, comma, 0.0952. Is this consistent with your decision to reject or fail to reject the null? Why or why not? So we concluded, so let's go up here. We concluded what? There wasn't enough evidence. So we basically concluded no change. No change. Okay? That means that we should be seeing 0 inside of this interval. And 0 is inside the interval. Remember, this interval goes from negative to positive, which means 0 is inside of it, no matter what, okay? So we concluded no change and 0 is inside the interval. So these two conclusions are the same. Okay, remember your notes from the chapters on differences. When we try to look for whether or not there was a change, we would look for all of the signs in this interval to be negative or all of the signs in this interval to be positive. If they span 0, we cannot conclude a change has happened. All right, I'm going to move on. Next page. Number 7. This review is long, okay? Centers for Disease Control state that in 2013, 17.8% of American adults were smokers. This is a P. That's from the population. Then it says, what is the probability in a random group of 100, that's a sample size, more than 20% of them are smokers. All right, so guys, they asked, what is the probability? So this is everyone's least favorite chapter 15. It's a sampling distribution problem, which means we must do this to start. That's a Q. Okay, So P is 0.178. So we would subtract from 1 to get Q, which means that Q is 0.8. Oh my goodness, guys, I don't feel like doing it in my head for some reason. 22. Okay, I can't even right now. 0.178. I need to make sure I got it right for you guys. Okay, 0.822. And N is 100. So our sampling distribution has to come first, where the center is at P, and we have to compute the standard deviation. So we're going to do that work in here. Usually I do that in steps. So 0.178 times 0.822 divided by 100, and I take the square root of the answer. So our standard deviation is, our model looks like this. 0.178, comma, I'm going to go to 4 decimal places. 0.383. Now we're finding the probability that more than 20% are smokers. So we want to find the probability that in the sample, more than 20% smoke. So this is my lower bound. Remember that I can even use decimals in normal CDF. So I go to normal CDF. My lower bound is 0.2. My upper bound is 1E99. My mean is 0.178, and my standard deviation is 0.0383. And I go to my calculator to compute the results. So second bars, number 2, lower is 0.2, upper is 1, second comma, 99. My mean is 0.178, and my standard deviation is 0.0383. Paste it and hit enter. Our answer here is 0.2828, and then we're done. Please review chapter 15 if this problem was not something that you either recall or something that you feel like you're going to be strong with on the exam. We'll have another one on means later on in the review. Okay, number 8. You think people's ice cream flavors are reflected by the following model. Look, it's a model that I believe is true, and it's a series of percentages. Look, 1, 2, 3, 4, 5, 6 different percentages. So this is going to be most likely a chi-squared test. Right? They gave me a list that I believe is true, and there's different percentages across the list, and there is no contingency table. This is going to be a chi-squared test for goodness of fit. So I'm going to begin by writing a table, because I'm going to have observed and expected data. Okay, and this will be list 1, and this will be list 2. I'm going to make myself a few notes, like vanilla, chocolate, strawberry, butter pecan, rocky road, and other. And then I'll make this a little bit longer so I can fit everything. So now I have categories to put all my information in, okay? So I surveyed 1,000 people, and I found the following preferences. 220 actually liked vanilla. These are what I observed, right? 255 liked chocolate. 190 liked strawberry. 170 butter pecan. 95 rocky road. And 70 other. So then we always check, do we have the right total? Yes. Okay, now the trick for the expected column, if we're given percentages, is to multiply the percentages times the total. So this would be the 25% we expect that like vanilla. I'm going to write the work down for each one. So this would be the 25% we expect that like chocolate. This is the 20% you expect that like strawberry. We expect 15 to like butter pecan. Only 8, which is 0.08, to like rocky road. And only 7%, so 0.07, to be others, okay? So then you want to multiply all of these. So here we get 250, 250, 200, 150, 80, and 70. And because we got those numbers from 1,000, they also total 1,000. So we put everything except the total into the list. So we're going to put this in list 1 and this in list 2. And before we do that, let's write out our hypotheses in words, okay? So this is a chi-squared GOF test where we put the observed into L1, expected into L2, and we run the test on the calculator. If that's an old calculator, you have the steps in the notes. If that's a new calculator, you can follow my steps. We're going to end up with a chi-squared and a p-value to make our conclusion. But over here, I'd like to write the hypotheses in words. What are we distributing here? Ice cream favorites, right? And we have a particular model. So this is when we can write the hypothesis. Ice cream preference is consistent with the model. And then we say there has been a change by saying that ice cream preference is not consistent with the model given. And then we can choose the answer based on the p-value compared to the alpha level. So let's go to our calculator. Stat edit. So I need to delete the first list, which was from problem 1. And I'm going to put my observed counts into list 1. And I'm going to put my expected counts into list 2. So 250, 250, 200, 150, 80, and 70. And now I'm going to run my chi-square test. So stat, arrow left, all the way up to the goodness of fit test. My observed are in list 1, my expected are in list 2. The degrees of freedom, oopsie, degrees of freedom is always the number of categories minus 1. So it's 1, 2, 3, 4, 5, 6. Minus 1 is 5 for our degrees of freedom, okay? So we go down, make sure that's degrees of freedom are 5, and we calculate. So I'm going to write down my chi-squared and my p-value. Chi-squared is 9.6792, and p is 0.0849. So I'm going to get this out of the way. We were supposed to go up here and use alpha as 0.05. So my p-value is 0.0849 compared to my alpha level of 0.05. It's greater, so we're going to fail to reject the null. Failing to reject the null means that we did not have evidence to show the change. So there is not enough evidence to show, and then I'm going to repeat my alternative. Ice cream preference is not consistent with the model. And then we're done. Next page. I wonder, it's getting long, guys. The video is getting long. Are we doing okay? If you need to pause and stop, let's do that. Okay? There's still several problems left that I want to do here. Here we're raising good cholesterol levels, and we've got 5 female volunteers that offered their measurements before they started running and after. So before and after, and it's the same 5 people. So this is paired data, which means I want to put before in list 1 and after in list 2. So it says, see if you can support the claim the average person's cholesterol level would be raised after running. Look, guys, that means that list 2 would be bigger than list 1, or list 1 would be smaller than list 2, which means that if we do the subtraction, which we have to do in our calculator, then we're looking for a negative difference, okay? So when we go to looking at this as a paired t-test, we would look at the null and alternative being, if there is no difference, then their difference is 0. But if list 2 is actually bigger, then when we subtract, we get a negative answer. Okay? So remember, this goes into list 1, this goes into list 2, and then we subtract in list 3. So this is when we do list 3 equals L1 minus L2, and I'll help you out there. So let's go ahead to our calculators together. Move this up. So we're going to go to stat in our calculators, clear your lists out, and we're going to enter the before 30, 34, 36, 34, and 40. And then oh shoot, whoops. Let me do that again. Sorry guys. All right, now into list 2, I'm going to enter the after 35, 39, 42, 33, and 48. And then in list 3, we have to arrow up. Make sure you're highlighting list 3, and then second L1 minus second L2, and I fill in my differences there. And remember that this is a t-test on L3. So let's write that down too. T-test on L3 with mu naught equal to 0. Okay? So let's go to our t-test. Stat, arrow left to test, and select option number 2. This is on data. Mu naught is 0, and change this to list 3. Make sure that you select less than and hit calculate. T is, I'm recording this, negative 3.0599, and the p-value is 0.0188. And we're going to compare that p-value to, I guess, 0.05 because there's no alpha level given. So we're going to go p-value equals 0.0188 and alpha is 0.05, we'll assume, which means this p-value is in fact less than the alpha level. So we can reject the null. If we reject the null, then there is evidence. There is enough evidence to show cholesterol would be raised after running. We did see a change, so we do want to talk about the cholesterol going up or the difference being negative, whichever one you'd like to talk about. All right, let's keep going. For several years, evidence has been mounting that folic acid reduces major birth defects. Results were published in the New England Journal of Medicine. For this study, doctors enrolled women prior to conception and divided them randomly into 2 groups. Stop there. This is going to be a 2 groups. One group had 2,701 women, and they took multivitamins containing 0.8 milligrams of folic acid. The other group had 2,052 women, and they only had trace elements. We had major birth defects in 35 cases when they did take folic acid, and only 47 when they did not. At the 0.01 significance level, do the data provide evidence to conclude women who take folic acid are at lesser risk of having children with major birth defects? All right, so let's get into this test. We've got 2 groups, and we've got a number of people who did have birth defects out of a total number of people. So this is a 2 prop Z test, which means in group 1, in group 2, we're going to need to identify the number of people who said yes and the total, so X1, N1, and in group 2, we'll need X2 and N2 to be able to run this test. So we want to read carefully. The first group mentioned is the group who did take folic acid. So I'm going to put a big F here and a big F with a line over it because remember it says the complement of folic acid. So 2,701 women took the drug while 2,052 did not, only had trace elements. We only had 35 cases in the group that did and 47 in the group that didn't. Do data provide evidence to conclude women who take folic acid are at a lesser risk? So we believe that group 1 is actually lower than group 2. So let's write that out in terms of hypotheses. We assume the two groups are equal, but if folic acid really does help, then its proportion will be lower. So we're going to record our Z and our p-value and make a conclusion. So go ahead to your calculator, stat, arrow to tests. It's a 2-prop Z-test, that's number 6. X1 is 35, N1 is 2701, X2 is 47, N2 is 2052. And we believe that, in fact, P1 is less than P2, so we'll make sure it's less than and hit calculate. Our Z is negative 2.6085, and the p-value is 0.0045. So now we're comparing that p-value, 0.0045, to alpha equals 0.01. That is actually less than 0.01, so we get to reject the null. There is evidence to show women who take folic acid are at a lesser risk. Using the hypotheses, describe type 1 error in the context or type 2. So type 1 is when you reject H naught, but H naught was true. Okay, so I'll write this one and then we'll reverse the order for type 2 because that's how it always works. So type 1 is I reject the null. So I'm going to go back up here and say I rejected this and I claimed the proportion had changed. So we claim folic acid helps, but it actually doesn't. Okay, so we claim it does help, but it doesn't. So women take a drug that's not helpful and they just still have the same risk of birth defect. And then type 2 is the opposite, where we would claim folic acid doesn't reduce defects, but it actually does. Okay, so we want to make sure that we don't make either one of these terrible mistakes that would hurt pregnant women and the potential effects that they might have. Guys, we're at question 10, which means we're almost done. Okay, so I'm flipping it over. If there's a difference in birth defect rate, find the 98% confidence interval for the difference in proportion of birth defects. So guys, if we just did a 2-prop Z test, then we go back and do a 2-prop Z interval, which is really low down. So it's letter B. It remembers everything, and we just need to make sure we change this to 0.98 and calculate. Okay, so we've got negative 0.019, and look at that, negative 7 times 10 to the negative 4. So that's the same as negative 0.019 and negative 0.0007. But both values are negative, meaning both are negative. That implies group 2 was the larger proportion. So this also matches the results to the test, saying that we found evidence of a change. Okay, there's no 0 in the interval, remember. Okay, I'm going to do number 11, and then I'm going to skip 12 and 13 because we've either done one very similar already in this video or it's in the mixed up examples, right? So number 11, college's data about incoming freshmen indicates they have a mean high school GPA of 3.4 and a standard deviation of 0.35. The distribution is normal, okay? They're randomly assigned to freshman writing seminars of 25 people, that's N. Now we're looking to find probabilities. So guys, this is way back in chapter 15 where this if the population looks like this and it's normal, then we can do this and make a sampling distribution for any size n. So if we know that from the population we have a GPA of 3.4 and a standard deviation of 0.35, and they ask that any student has a GPA greater than 3.5, then we can use the population data. This says 3.5 is my lower bound, 1E99 is my upper bound, my mean is 3.4, and my standard deviation is 0.35. I'm going to go to the calculator and go to second bars, number 2, 3.5, 1E99, 3.4 is the mean, and 0.35 is the standard deviation. Paste twice to get our answer, 0.3875. Now, this is the sampling distribution part. This says the probability that one of the groups has an average GPA, okay? So then we're still doing greater than 3.5. So now it's the probability that the group's GPA, the sample GPA, is greater than 3.5, which means we need to find this, our sampling distribution for n equals 25. So we're going to make sure that our mean never changes. It's still 3.4, but our new standard deviation needs to be shrunken. So this would be 0.35 divided by the square root of 25. The square root of 25 is 5, so we get 0.07. Now I approach this the same way, just with a smaller standard deviation. Normal CDF, 3.5, 1E99, 3.4, but now I shrink my standard deviation to 0.07 and run this. So second bars, number 2, and all we have to do is change the standard deviation and paste it again. And my answer drastically changes, shrinks. Okay, again, number 12 is a problem similar to one we've already done today, so you can go ahead and look at the solutions for your help with that. And number 13 is from the mixed up examples on one of my previous videos. I think that's page 17 of the packet. There's one more. And I'm not going to do this problem with you. I just want to explain number 14. We've actually already done a problem very similar. It's another chi-square goodness of fit test, but this is a different type of goodness of fit. So bear with me. We have 425 children surveyed, and they have 5 professions to choose from. They chose, 80 of them chose teacher, 105 doctor, 70 lawyer, 70 police officer, and 100 firefighter. Obviously, they preferred some over the other. Test whether their preferences reflect a real difference at the 0.05 level. Okay, so this is the chi-squared test where the model given for goodness of fit is that this is uniform or the same in all categories. So when you make your table observed and expected to put into L1 and L2, which is really similar to number 8 that we did together in this video, when we go to make this table, we want to write down like something to give it away. Teacher, doctor, lawyer, police officer, firefighter, right? And our observed are the values found. So 80, 105, 70 said lawyer, 70 said police officer, and 100 said firefighter. So triple check that this really is 425. And then to find these values, we take the total and divide by the total number of categories because we think it's uniform. Okay? So then this would be 425 divided by 5 gives me 85 in every single category. Okay? And then we run a chi-squared, let me write, test for goodness of fit, where L1 is observed, L2 is expected, and the degrees of freedom are the number of categories minus 1. We gave them 5 choices, so the degrees of freedom are 4. Okay? Now, when you write the hypotheses for such a test, you can actually write them in the same exact format. Like, I would write in something like the distribution of the distribution of profession is consistent with the model, or future profession is not consistent with the model. Something like that, where we know the model just states that it's uniform. It's still a model. So you don't have to alter your language just because we're talking about a uniform distribution. You do have to alter how you fill in the expected value column. So there's 2 different kinds of chi-squared tests for goodness of fit in terms of how to calculate expected. Now you can go to the solutions and finish up this problem by making sure you get the same chi-squared value, p-value, and a similar conclusion as I did. Good luck on the test. Good luck reviewing.